And the reason why it's Chem 200 stuff is because it's a simple titration. Whenever you have a simple titration between a strong acid and strong base, it is not equilibrium. It is stoichiometric. So if you don't remember your stoichiometry, please review that because that's going to be important for this particular discussion. Okay. Um, go ahead and start the slideshow here. So whenever you have an acid, it's going to dissociate and form its conjugate. Whenever you have a base, it'll also dissociate and form its conjugate. But if you have a strong acid and strong base, then the key products for these chemicals are H plus and OH minus. And in a strong acid, strong base situation, what you have is a neutralization reaction. You form water. And that's what you see right here. Okay, that's what you see right here. You see this right here. The reaction between an acid and base forms water and then the salt. So this is a typical reaction, hydrochloric acid and sodium hydroxide, you form water and sodium chloride, okay? The amount of hydronium and hydroxide that remains, let's say you're doing a titration, and this is an acid, let's say we have 100 acid here, okay, and you're adding base, and let's say that you add 50, and let's say that this is moles, and this is moles, hydroxide here. Then what will happen is that the hydroxides are the limiting reagent. It's going to react with 50 of the acid and form 50 water molecules, but what's left behind is 50 H plus that went unreacted. That chemical right there, and this is key, is going to dictate the pH of the solution. Whatever that concentration of what remains unreacted, it'll be the moles over the volume, and the volume is the new volume after you added the hydroxide. That'll be the concentration of the hydronium, and you use that to calculate the pH. Okay, so that's the stoichiometry part of this particular discussion. What we're doing here is simply a titration between a strong acid with a strong base or a strong base with a strong acid. Your first job when you have this type of problem is calculate the moles. Your second is to figure out which is the limiting reagent. And then your third is to figure out the concentration of the excess. And the concentration of the excess, whichever remains, either the acid or the base, will determine the pH of the solution. So if you over titrate and you add more hydroxide than hydrochloric acid, the hydroxide is going to be the excess because you've added more. And so what you need to do is you need to calculate the hydroxide that went unreacted divided by the total volume now in that solution. And that's the concentration of your hydroxide. If you have the concentration of the hydroxide and you take the negative log of the hydroxide, you have the POH. And you can calculate the pH from subtracting 14 from that POH. Okay, remember that pH plus POH equals 14. Of course, we're assuming that it's water at 25 degrees and the water is uncontaminated. So let me go back real quick because there was something that, this right here. Analysis is a stoichiometry problem only if a strong acid is combined with a strong base. Only. That's very important. Okay. If you have a strong acid combined with a weak base, the first part is stoichiometric because the strong acid is going to dictate that it takes all its hydrogen, and the second part is equilibrium. We'll be talking about that part on Wednesday. So this is a typical titration. Titration, you basically have the analyte. The analytes are the chemicals that you're analyzing. That's why it's called the analyte. You basically have a fixed volume. You introduce that fixed volume via a volumetric pipette. The next thing you do is you prepare your titrant. Your titrant is going to be in the burette. And you know what the concentration of that is because it's controlled. You don't want to use a chemical in which you don't know the concentration, because then that defeats the purpose. And then you also want to make sure that you use a strong acid or a strong base. Don't use a weak acid or a weak base, because that only complicates the analysis. If you have strong acids or strong base, you know that it's going to demand that the hydronium be accepted by the base, the analyte base, or if you have a base there, you know that the base is going to dictate that it removes as much of the hydronium from that analyte acid. Okay, that's why you want to have it controlled. And then you're going to titrate it to, usually you put an indicator in there to tell you that you've reached the point where the hydronium ion concentration is equal to the hydroxide ion concentration. The hydronium usually is your analyte, the hydroxide is generally your titrant. When those two are equal, then you have no excess hydronium or hydroxide. And generally, an indicator there will change color when that happens. An indicator changes color at the endpoint. The endpoint is experimental. That's where you see a color change. The equivalent point is the theoretical value in which hydronium is equal to the hydroxide. Okay, these two should match, but sometimes there's a lag. Remember, sometimes the experiments doesn't follow the theoretical precisely, and that leads to experimental error. Okay. So there was a question here. Is that the same as planes, or are those masks different? Not really know, don't really know what that question is referring to. Maybe you can clarify that for me.
That was for the bag. I think they were talking about the bag.
The bag?
Point.
Which one?
They were talking about the bag. You were talking about like
oh yeah,
exhaling.
Right. Sorry. Yeah, it's about when you have when someone's hyperventilating, they take a paper bag and they breathe in it. Okay, and they breathe in and out, because what they need to do is they need to recirculate the carbon dioxide that's coming out of their body, and they need to put it back into their body, so that now it basically decreases the reaction in which carbonic acid breaks down to carbon dioxide and water. So by breathing into a bag, what will happen is that that reaction goes into the reverse. You maintain your carbonic acid in your body, and then that excess will form bicarbonate. And then remember, this is for the alkalosis situation. When carbonic acid breaks down to bicarbonate, it generates hydrogen ion, so that your blood pH goes from a higher value to a lower value. Okay, so hopefully that, again, I apologize for not seeing that chat earlier. That's what that means. Let me go ahead and continue here, because I want to finish this up. So these are acid-base indicators, and we use different indicators because sometimes the endpoint isn't exactly at 7. We think it's going to be 7, but it's not. Okay, sometimes the endpoints are going to be lower than 7 or higher than 7, depending on whether you have a weak acid or a weak base that you're analyzing. Because remember, the conjugate of a weak acid will convert over to a base. And so if you, in your titration, eliminate all the acid, let's say you introduce hydroxide, then the only chemical left in your beaker after you've neutralized that weak acid is that conjugate base. And guess what the conjugate base will do? It will undergo hydrolysis and cause that solution to be basic. Okay, because the weak base will now react with water, the water is going to give up its hydrogen to the conjugate of that original weak acid, and in the way of giving up its hydrogen, it forms hydroxide. So the solution is basic. And you guys know this from our discussion of salts. Remember salts? If you have sodium acetate, the acetate ion will react with water, and the water will give up its hydrogen to this conjugate base and form a basic solution. This is called hydrolysis. And so if the solution is going to be basic at the equivalence point, then you want to use indicators that are going to be on this side, not this side, because the equivalence point is going to be, or the end point is going to be higher than 7. So that's the reason why we have these different indicators. Let me go ahead and finish this real quick. And I'm going sort of fast here just because a lot of this is not new. A lot of this is stoichiometry. And I really want to make sure I end this so that I can go into Wednesday talking about the bulk of chapter 17. This is phenolphthalein. Phenolphthalein generally has this structure, but what happens is that this bond breaks when it goes from an acidic solution to a basic solution. So under a basic solution, what will happen is that there's going to be a hydrogen that's donated to the hydroxide that comes in and then breaks up to this configuration. When it's this configuration, it goes from clear to pink, okay, or lavender. And that's what that tells you, that you now don't have excess hydronium or excess hydroxide. The solution now is at its equivalence point and you stop your titration. Okay, so let me go ahead and this structure, by the way, is just the structure of phenolphthalein, and that's a movie, and you guys can see that, but I don't have time to show the movie. You guys already know about titration. I want to talk about this because this is a thought experiment, and this is the last thing I'll talk to you guys about. This is a thought experiment of a strong acid, strong base situation. So what we have generally is we have a analate, and our analate is a strong acid. Let's say HNO3. Okay, and let's say that we have 100. Let's do it molecules or moles of HNO3. So that's what we have right here. Okay, we have 100 moles of H plus. Initially, before we add any base, before we even do the titration, we want to know the pH of that solution. Well, the pH of that solution is just the amount of hydrogen ion moles in the volume. And if we have the concentration, we can calculate the pH. And so that's what you see right here. The pH is equal to the moles of the acid divided by the total volume, and that's just the volume of the analate that you start, the negative log. So before you add any base, what will happen is that you have a pH of that solution. Now we start our titration. And let's say that out of this 100, we add 20 moles of base, hydroxide. Well, here it is right here. You have 20. That means this is the limiting reagent. 100 minus 20 is 80. So we have 80 hydrogen ions remaining. Of course, we produce 20 waters because the hydroxide and the hydrogen ion produces water, but the concentration now of the hydronium is 80 divided by the new volume, and the new volume is the original volume of your analate plus whatever volume you add from the titrant. Let's say you add 5 mils and you started with 25 mils here, then the new volume would be 30. So the pH of that solution would be the acid moles that you have divided by the new volume. The volume is constantly changing, and if you take the negative log of that, then you've got the pH. If you add 50, then that means you've got 50 hydrogen that remains unreacted, and the pH is just 50 divided by the new volume, the negative log of that. Well, what happens at the equivalence point? At the equivalence point, you added 100 hydroxide. Well, there are no excess hydronium or hydroxide at that point. So what is the pH? It can't be 0. Well, the pH is dictated by the ionization of water. Water will self-ionize, and if you've got pure water here at 25 degrees, then that pH is 7. Okay? So remember, you're always calculating how much remains, because that'll give you either the pH, or once you have an excess of base, see here, the limiting reagent now becomes the acid. And what you have is excess hydroxide that went unreacted. What you need to do is you need to figure out how many moles of excess hydroxide went unreacted by the new total volume. It's always based on the new total volume. And if you take the negative log of that, you've got the POH. And of course, if you want to calculate the pH, just subtract 14 from the POH. And if you add more excess base, you've got more excess hydroxide, and you can calculate the POH of that. But that basically is how you would solve the titration of strong acids and strong base. It's all stoichiometric. Notice that I didn't mention any Kas or Kbs in that problem. I just figured out how much excess remains, and the excess dictates the pH or the POH. And so that's what you see in these problems right here. This is the workout of all of that. Okay, here's my hydrochloric acid. This is my limiting sodium hydroxide. What remains is going to be right here, the final, because that's what went unreacted. The new volume is going to be whatever volume you have right here. So if you take 2.5 millimoles divided by 75, that's the concentration of the acid that went unreacted, and then you can calculate the pH directly. So follow along these right here, because again, it's not equilibrium, it's a stoichiometry. So I'm not going to really talk more about this other than to show you how those calculations are made, because in the end, you're going to generate a titration curve, and the titration curve is going to be a pH 1, pH 1.48, pH 3, pH 7, 11, and 12. This is your pH value, and this is the base volume right here. And what you guys are going to see is a titration curve that looks like that. And that's what you see in this picture right here. Okay. So I apologize for rushing through that last moment, but I just want to make sure that I put it out there. And then for next time, there's more of the strong acid, strong base situation. I want to cover 17.03, which is the last section and probably the most critical section in chapter 17.